Welcome to Yengel's algorithm series for absolute beginners. In today's video, we'll learn about merge sort. The merge sort algorithm follows a divide and conquer strategy. Let's dig deep to find out how exactly this merge sort works. For the sake of this demonstration, we will be working with this following input list. We'll employ merge sort to sort the input list in ascending order. Since this follows the divide and conquer strategy, we'll divide our input into smaller problems and then solve them one by one. First, we'll divide the input into two equal parts. We take these two broken halves and divide them further. We repeat this process until we have reached the most basic building block of our list, which are the numbers themselves. We started off with a single input list and we divided it until we got a bunch of lists, each containing exactly one element from our input list. We have successfully divided our input list. Now, these output lists are considered to be sorted because they have just one item in them. If a list has only one item in it, it is a sorted list. So, by dividing our input list into its most basic components, we have produced 6 different output lists, each of them sorted. It's time to merge our sorted list back into a single list. Let's remove all the distractions from our slide so that we can get a clear picture. Now we can see a clear path which the merge operation will follow. Remember, every time when we divided our input list, we produced a left and right component. First, we set our sight on the innermost left node. We check if the list in our innermost left node is a sorted one or not. What do you think? Is it sorted? Yes, it is a sorted list. Our list has only one element at this point, so it is a sorted list. Since our left node contains a sorted list, we set our sight on the innermost right node. We find that it is a sorted list as well. It seems both our inner nodes have sorted list in them. Let's merge them. For merging, we compare the values in our sorted list and we insert them back into an empty list. The order of their insertion ensures that we have an ascending sort. This sorting action has taken us a level further towards the top. At this level, we have two lists that are sorted. Now we have to merge them back into a single list. We compare their values one after another and insert them back into a new list in ascending order. We have successfully sorted one half of our input list. The second half of our input list has not yet been sorted. Let's fix that, shall we? We travel to the innermost left node and check if it is sorted. We check the same for the right hand side node. If both the lists are sorted, then we perform a merge operation. This leaves us with two sorted lists on the same level, so we perform the compare and insert operation all over again. Well, it seems we are back to square one. We are left with two sorted lists residing on the same level. Let's merge them by comparing their values and inserting them into a new list in ascending order. All the leftover values will be inserted into our output list because, hey, they're already sorted. There we have it. We have successfully sorted our input using merge sort algorithm. If we were to sort this input using bubble sort algorithm, it would have taken us 15 comparisons to sort the input. Merge sort achieved the same result with just 9 comparisons, and this gap keeps widening for large inputs. Let's take a look at how merge sort has been implemented in Python. The highlighted part of our code divides the input list into its most basic components. Let's try and understand the function of each line in this block. We check if the length of our input list is greater than 1. There's a brilliant reason for this check being placed here. We'll come to know about it shortly. We find the middle value along which we have to break the input list. Once the middle value has been determined, we separate our input list into a left and right component. The separation happens at the calculated middle index. These steps must be repeated until we have divided our input list into its most basic components. And how do we do that? We send our divided input back into our function. This is called as recursion. This recursion continues until our input cannot be divided any further. Let's see how recursion happens. We are sending the left component of our divided input back into our function itself. This creates a totally new instance of our function, with input being the left component of our divided input list. Let's add a landmark to our code. This helps us to keep a track of where this particular instance of our code should return once it has performed all the necessary recursions. We check if the length of our new input is greater than 1. If so, we find the middle index value of our input list. We split our input into a left and right component along the middle index value. It seems we are going into the recursion process all over again with the new left component. Let's add a landmark at this instance and perform the recursion again. We check if the length of our input is greater than 1. It seems it is not greater than 1 this time. This means we have reached a basic component of our input list. We don't have to perform any further action. This instance gets terminated. The program moves back to our landmark in our previous instance, and it continues its journey from there. We are going to send our right component into a recursion loop. Let's add a landmark to this instance. The program creates a new instance for this function and performs all the operations there. We check if the length is greater than 1. We then proceed to find the middle index of our input list. We divide the input list into its left and right component at the middle index. We once again go into a recursion. We add a landmark and move on with our recursion. The length of our input is not greater than 1. It means this node contains a basic component of our input list. So the current instance gets terminated and we move back to our previous instance. The recursion happens once again for the right component. After performing all the steps, we terminate the current instance and move back to the previous instance. Finally, we have reached the second section of our code. This part takes care of all the merge operations. Do notice that we still have landmarks in our code. This reminds us that we are still working inside a recursive instance of this function. The first block of this code compares the value between two sorted lists and insert them into an empty list. The subsequent blocks instructs our program to paste the leftover value into our output list. This instance of our function has been executed, so it will get terminated. We then move on to our last pasted landmark and then continue the execution of that particular instance. The highlighted code is yet to be executed in our landmarked instance. The first part of this merge section compares two sorted lists and pastes them into an empty list. All the remaining values in our sorted lists will be pasted into our empty list. After completion of this instance, it gets terminated and we move on to our previously landmarked instance. After performing this recursive operation, we have sorted half of our input list. It's time to sort the other half. We'll perform the same recursive operation all over again on our right node. After the second recursive operation, we have successfully sorted the second half of our input list. We still have our highlighted code block yet to be executed in the main instance of our function. This code block merges the previously sorted lists into a single sorted list. There we have it. We have successfully sorted our input list using the merge sort algorithm. See you guys in the next video. If you guys like our work, consider subscribing to our YouTube channel for more educational content.